Scientists have made a staggering discovery. A planet circling the Sun's nearest neighbor, with temperatures that could allow liquid water to flow. What will it take to go there, to explore it? The answer is speed. Laser-driven spaceships, antimatter engines, warp drive, right out of science fiction. How far? How fast can our technology take us? It's a journey that has lasted a century. A spacecraft approaches its destination, a planet beyond our solar system, and a future beyond our imagination. Touchdown will mark a milestone in our eternal quest to expand our horizons, to explore, and to survive. It's not the first time we've struck out into the void against all odds. For much of our history, the oceans were the great unknown. Several thousand years ago, a seafaring culture emerged in the Southwest Pacific. Riding ocean and wind currents, the Polynesians sailed east, navigating by the stars, the moon, and the sun. Over centuries of time, they claimed the Pacific Ocean, island by distant island. It was one of the most expansive migrations in human history. Their furthest reach, Easter Island, was over 2,000 kilometers from the nearest land. Today, we have begun to reach beyond our planetary shores. Across distances so vast, we measure them in light years. That's how far light travels in a year. Almost 10 trillion kilometers. Out in the southern sky, just over 4 light years away, you'll find our sun's nearest neighbors, a dim red dwarf star called Proxima Centauri. And a pair of sun-like stars called Alpha Centauri. Go beyond them, and you've entered the local bubble. A giant, empty region cleared of gas by a star that exploded long ago. Within this bubble, 50 light years from Earth, are 150 stars bright enough to be seen with the naked eye. Nestled among them are 2,000 smaller stars, visible only with a powerful telescope. How many have planets? Could any serve as stations on our way out to explore the galaxy? Our first stop would be a planet discovered in orbit around the star nearest to Earth, Proxima Centauri. About 1/3 larger than Earth, it's a very different kind of planet. One side is dark and freezing. The other side, forever bright and warm, always faces its sun. Could life flourish here? Could humans survive? The key is whether there's an atmosphere and water on the surface. These may be signs that there's a climate and temperatures moderate enough to support life. If Proxima b, or any other planet in the solar neighborhood, proves to be habitable, the call will certainly be heard to mount an expedition to see and explore it up close. But to get there, in the short course of a human lifetime, will take whole new types of spacecraft we have yet to build. Whole new designs that can propel us to extreme speeds. The discovery of Proxima b was part of an intensive campaign to find worlds like Earth in the neighborhood of our Sun. Increasingly, the hunt for planets combines the enormous light-gathering power of a new generation of giant telescopes on the ground with a growing fleet of telescopes in space. The Transiting Exoplanet Survey Satellite, or TESS, is designed to monitor more than 200,000 bright stars. Astronomers expect they will find 500 Earth or super-Earth-sized planets in this part of the galaxy. TESS will be joined by the long-awaited James Webb Space Telescope, with a segmented primary mirror almost 3 times larger than that of the Hubble Space Telescope. It will allow scientists to search the light of nearby stars for silhouettes of planets. The W1st Observatory will follow in the mid-2020s. With the resolution of Hubble, it will take in light from a region 100 times larger. It may well produce our first direct images of Earth-sized planets. By deploying a coronagraph that blocks a star's glare, it will be able to hone in on light reflected by planets. With these images in hand, the astronomers will attempt to measure surface temperatures, detect atmospheres, and look for the chemical signatures of life. In the meantime, they are devising whole new tests of habitability. One group used the Hubble Space Telescope to probe a series of 7 planets recently found orbiting an ultra-cool dwarf star 40 light-years away, called TRAPPIST-1. Each of these planets is roughly the size of Earth. 3 orbit within the habitable zone, at a distance from the parent star and with the right temperature to support liquid water. What are the chances they actually harbor oceans and rivers and lakes? Red dwarf stars like TRAPPIST-1 are known to emit large and violent flares. Over time, solar radiation acts to split molecules of water in the atmosphere. Hydrogen atoms liberated in the split then waft into space, leaving the oxygen to bind with rocks on the surface. This same process has been documented on the planet Mars. In its early years, there was enough water to carve networks of river and lake beds. Over time, these stores of water disappeared, along with Mars' chances of nurturing life. To find out whether the planets of TRAPPIST-1 had been stripped of their water, astronomers measured the amount of ultraviolet light striking them. It's an indication of their exposure to solar flares. They found that the innermost planets are bathed in ultraviolet light and are most likely bone dry. By contrast, the outermost planets have been spared the radiation. It's possible they have kept the stores of water acquired during their birth, whether liquid or ice. Based on a statistical analysis of solar systems discovered so far, one study estimates that there is at least one planet like Earth within 20 light years. Astronomers may have already found it. Each night in this control room at the La Silla Observatory in Chile, astronomers conduct the world's most intensive hunt for planets in the neighborhood of the Sun. They work with an older telescope commissioned in the year 1977. It has a relatively small mirror at 3.6 meters in diameter. But it's outfitted with spectrographic technology that allows astronomers to finely parse the light of nearby stars. It does this by recording subtle shifts in the light caused by the gravitational tug of $79,000 years from now, it will become our Sun's nearest neighbor. Inevitably, the discovery of planets around nearby stars has spurred debate about the imperatives of an interstellar mission. The physicist Stephen Hawking is one of a growing number of scientists concerned about a cloud of uncertainties surrounding Earth's future. Pollution, overpopulation, war, climate change, rising seas. We have no choice, they say, but to develop the technologies needed to not only travel to other solar systems, but to survive in alien realms. The dream of settling distant worlds is as old as the rocket itself. Back in the early years of the 20th century, the Russian space visionary Konstantin Tsiolkovsky believed humans would one day ascend to the stars. They would evolve into a whole new species he called Homo cosmicus. Tsiolkovsky laid out the basic physics of the rocket. His famous rocket equation describes the basic principle of acceleration. It's the force of mass expelled at high velocity out the back of a rocket versus the overall mass of the rocket. Decades later, in the 1960s, with the space age in full swing, another Russian scientist, Nikolai Kardashev, described spacefaring civilizations as the product of a long-ranging technological evolution. He defined Level 1, a planetary civilization, as one with the ability to tap into energy equivalent to that of the sun striking our planet. At this basic level, a civilization would exceed our current energy-generating capacity by 5 orders of magnitude. It may take us centuries to advance that far. It may take thousands or even millions of years to reach Level 2, the ability to harness the energy equivalent of a star, or Level 3, the energy of a galaxy. In theory, a civilization with that level of sophistication could wander the galaxy, mining raw materials from planetary bodies, while generating energy from technologies we can scarcely imagine. Advancing to that level does not mean we can afford to abandon Earth. According to a recent rethinking of Kardashev's theories, radical advances in technology are not likely to liberate us from a dying planet. In this view, interstellar flight will flow from successful efforts to solve humanity's growing energy needs, with technologies that are more efficient, powerful, and safe. Indeed, radically more potent fuels and engines could even pose serious dangers to the very environments that allow us to develop and test them. To advance toward a planetary civilization, we'll have to produce energy in ways that safeguard our base of operations, Earth. What leaps in science and engineering will interstellar technologies depend upon? How far? How fast can they take us? The speeds we can reach depend on the technologies we employ and the power we put into them. power is often measured in joules, the amount needed to lift a 100-gram object 1 meter against Earth's gravity. The metabolism of an average person at rest produces 100 joules per second, or 100 watts. That's the same as a light bulb. An elite runner traveling at 40 kilometers per hour generates 1,500 watts. Using the technology of a bicycle, we use that same power level to top 66 kilometers per hour. On the ground, this is the ultimate. A race car can reach speeds of 350 kilometers per hour. With an engine that converts the potential energy packed into gasoline, about 40 million joules per kilo, to the kinetic energy of motion. It's held back by friction from the road and the air. One way to fight friction: soar into the upper atmosphere. The SR-71 Blackbird flies at 3,500 kilometers per hour, 10 times faster than a race car. As much power as a jet can muster, a full tank buys only a few hours of flight. The problem is even worse when it comes to rocketing into space. To rise into Earth orbit, the giant Saturn V rocket must hit 28,000 kilometers per hour, almost 10 times faster than a jet. But the faster it goes, the more fuel it burns, the more it has to carry. To get Apollo astronauts into space and on their way to the moon, a Saturn V rocket had to lug 16 times its weight in fuel. As inefficient as chemical rockets are, they have served the vast imperatives of the space age. Since the 1960s, we've used them to launch thousands of satellites for communications and military purposes, for studying the Earth and peering into space. And we've used rockets to send a succession of astronauts into Earth orbit. The now retired Space Shuttle served as a platform for research, for launching and servicing the Hubble Space Telescope, and for building the International Space Station. A successor to the Russian Mir and American Skylab stations, the International Space Station began to take shape in 1998. Through more than 150 manned and unmanned missions, it has become the largest collaborative engineering project in history. This sprawling structure hosts a complex arrangement of modules and nodes, and a network of labs and living areas. Here, astronauts are learning to live for extended periods of time, apart from the climate systems, resources, and comforts of our home planet. From Earth, rockets deliver resupply missions up to 6 times each year. These unmanned capsules from Russia and the United States carry hundreds of meals, new equipment, and scientific experiments. The International Space Station has become a hub for zero-gravity science. At any given time, the crew is conducting pointed research into life support systems and preparing data for publication in science journals. Proponents of this work see it laying the groundwork for longer and more ambitious manned missions. There are a host of challenges to overcome. Beyond recycling waste and the internal atmosphere, life support systems must include the ability to grow food. On missions far beyond Earth, living compartments must protect against solar radiation and cosmic rays. Once these problems are solved, some proponents envision the construction of bases in orbit around the Sun, with factories or supply hubs to support a network of remote colonies. Whether we send people to explore Mars or to mine rare minerals on asteroids, we'll have to overcome the power and speed limits of the space age. Right now, because of the amount of fuel needed just to send a rocket into space, most long-distance spacecraft can only coast to their destinations. The twin Voyager spacecraft got around this by using the pull of Jupiter's gravity as a planetary slingshot. Racing out at 62,000 kilometers per hour, more than double the speed of a Saturn V, Voyager 2 became the first spacecraft to exit the solar system. But as fast as it's going, it will need another 73,000 years to reach Proxima Centauri. To make long-distance space travel efficient, whether it's humans or robots making the journey, we'll have to reinvent the rocket. The search for faster, more advanced spacecraft began in the 1960s, in the shadow of the nuclear arms race. Nuclear bombs release energy by splitting the atom. Imagine if that potential could be harnessed to propel a spacecraft. Scientists tested a whole new type of rocket, a vehicle propelled by small nuclear explosions. They envisioned an orbiting space station as the launch pad for the Orion spacecraft. A series of controlled nuclear blasts set off behind the craft would accelerate it to 10% the speed of light. Orion would have been able to reach Proxima b in just over 4 decades. Plans for this spacecraft never got off the ground. The technology was unproven and perhaps unsafe. In the 1970s, with interstellar flight still in their sights, a group of British engineers designed a 200-meter-long craft called Daedalus. It would use another type of nuclear power: fusion. It's the energy that lights up the sun by forcing atoms together under immense heat and pressure. Just a gram of fusion fuel could yield energy in the range of 200 billion joules. The idea was to produce an extremely hot gas that would propel the craft by blasting out the back. After accelerating through 2 stages, it could cruise along at 12% the speed of light. But this required Daedalus to carry more than 40,000 tons of fuel, and there'd be nothing left to slow it down. As it flew past its target at 129 million kilometers per hour, it would deploy a fleet of robotic explorers to go in for a quick look. Daedalus was never built, but the completeness of the design has inspired new generations of dreamers. Today, one group of scientists believes it may have a way to reach Proxima b more efficiently. The concept begins with a solar power generating station orbiting Earth. It's lined with lasers, each aimed at a tiny spacecraft, a futuristic version of that Polynesian sailboat. The force exerted by each laser beam is small, but together in frictionless space, they can propel a space sail with staggering success, to 20% the speed of light. In just 20 years, a fleet of laser-powered kites approaches Proxima b. They send their data, bouncing from one craft to the next, on a 4-year return journey to Earth. If Proxima b proves a worthy destination, there are technologies on the drawing board that promise an even faster ride. What if we could tap into the stuff of science fiction? Antimatter. It's the product of high-energy radiation that rips through our solar system. When cosmic rays smash into atoms in our upper atmosphere, they create a spray of particles of the opposite charge. If we can't capture antimatter particles in orbit, we may find a way to produce them on Earth. Down at CERN, the giant physics lab on the border of France and Switzerland, scientists are creating antimatter as a way of studying the nature of matter and how it emerged in the earliest moments of time. Using the Large Hadron Collider, they accelerate atoms to nearly the speed of light and blast them together to release their fundamental constituents. But the antimatter yield is so small that the cost of producing just a gram's worth is estimated to be upwards of $100 trillion. And the stuff is so volatile that storing more than a few atoms at a time remains a significant challenge. Our ability to produce such an energy-dense fuel raises basic questions about the imperatives of interstellar flight. It recalls past debates about nuclear power, whether we can safely acquire, store, and put it to use. Do the dangers outweigh the benefits? One thing's for sure: more Earth-friendly alternatives, such as geothermal, solar, and wind, won't transform us into a planetary civilization. And they don't have the explosive power to get us to Proxima Centauri. Antimatter might. It is the most powerful fuel known, with about 2 billion times more energy than conventional rocket fuel. In contemporary spacecraft designs, protons and antiprotons are isolated with magnetic fields. They're channeled in parallel to a propulsion chamber. Where they collide, the streams annihilate each other. The blast creates a high-energy beam that pushes on a magnetic field within the craft, accelerating it forward. Though it would only take 1,000th of a gram to fly to Saturn, the craft would need to carry tons more to get up to interstellar speeds and reach Proxima Centauri within a human lifetime. Such a potent fuel brings serious hazards. The high temperatures produced by an antimatter engine would be enough to destroy the spacecraft. It would have to be made of materials not yet invented that can radiate that heat into space. Setting out on its journey, the spacecraft must navigate an obstacle course of interstellar objects. If it meets a meteor, it uses a battery of shields to pulverize the object and whisk it away. If the craft plows through a cloud of dust, it's buffered by a protective magnetic field. As it finally closes in on its target, it releases a probe, our cosmic envoy. Powered by its own antimatter engine, firing in reverse, the probe would need to spend years, even decades, slowing down. Even at these speeds, the mission is probably too long for any human to go along. Imagine a time in the future when the stars are literally at our fingertips. A spacecraft maneuvers into an orbital station in preparation for launch. It's a testament to science, conceived on a stunning theoretical frontier, with engineering far beyond what we know today. It's based on a mind-boggling discovery by Albert Einstein, that gravity is actually the warping of space by massive objects. What if a spaceship could manipulate this strange cosmic trait to pass between the folds of space and time. Such a spacecraft would run on exotic forms of matter not yet discovered, and the equivalent of all the electric power generated by the United States. Welcome to Warp Drive. In theory, this ship could go faster than light as it traverses the galaxy in a cosmic bubble. Don't book your flight just yet. Building a spacecraft like this will take breathtaking advances in science and technology. But who can say what challenges human ingenuity will overcome? What ideas or technologies will one day propel us forward? When or if we do reach for the stars, the impulse will come not from a struggle to survive, but from a sense of wonder at the limitless variety of a living universe. Imagine the day, hundreds or thousands of years in the future, when a starship arrives at Proxima b or another destination. Whether it carries humans or not, we'll no doubt send an unmanned probe down to give us our first up-close look. It might land using the same technologies we've perfected in our day, at the dawn of planetary exploration. Sensors will probe the alien landscape. Artificial intelligence will interpret what they see. The planet's soils, its atmosphere, perhaps the presence of life. Steadily, a new world will surrender its secrets. With each revelation, we'll reflect on the odyssey that brought us here, and how it began in the discoveries and dreams of generations long past.